So in this video we will start chapter 6, Finite Abelian Groups and their characters. We know basic theory of groups. We know what is a group. A group is a set with some binary operation which is associative, and there is identity element and there is inverse. And similarly, if commutativity holds, then we say it is a abelian group. So we know elementary basic theory of groups, and we know for a finite group every element has finite order. In fact, if G is a finite group and A is any element of G, then there always exists a positive integer n less than equals to order of G, such that A raised to n is equal to E. So now we define indicator. If G dash is a subgroup of finite group G, then for any element A in G, there always exists an integer n such that A raised to n belongs to G dash. If A is already in G dash, then this n can be taken to be 1, and if A does not belong to G dash, then n is the order of, n can be taken to be the order of A, because if n is order of A, then A raised to n is just identity element, and that always belongs to G dash. So we can say there always exists an integer for which A raised to n belongs to G dash. So however, there maybe exist some smallest positive power of A which lies in G dash, which is less than order of A. So we define the smallest positive integer n such that A raised to n belongs to G dash is called the indicator of A in G dash. So we have a theorem regarding this, theorem 6.6 in the book. Let G dash be a subgroup of a finite abelian group G, where G dash is a subgroup of finite abelian group G, and G dash is actually proper subgroup, which means G dash is not equal to G. So we choose an element A in G which is not in G dash, and we choose H. We take H to be the indicator of A in G dash. Then this set G double dash, which is collection of all the products x into A raised to k, where x is an element of G dash and k is any integer between 0 and h minus 1. Then this G double dash, this is also a subgroup of G which contains G dash, and moreover the order of G double dash, this is h times the order of G dash, or we can write in this term G double dash h times G dash. So let us prove this theorem. Firstly, we have to prove G double dash is a subgroup of G. So we will prove the subgroup criteria. So firstly, we test the closure property. So let us take two elements in G double dash. Let us say x ak and y aj. They belong to G double dash. So we have to prove their product also belongs to G double dash. So if these two elements belongs to G double dash, then x and y belongs to G dash, and k and j lies between 0 and h minus 1. Now because G is a abelian group, so the product of these two elements, x into ak, y into aj, can be written as x into y a raised to k plus j. Now because of this k plus j, this is an integer, and when we divide it by h, we get two unique integers q and r, where q is quotient and r is remainder. So k plus j can be written as qh plus r, where r is remainder, so it is strictly less than h. So it means this a raised to k plus j can be written as a raised to qh plus r, which means a raised to qh into a raised to r. Now a raised to h belongs to g dash, because h is indicator of a in g dash. So a raised to qh, this also belongs to g dash, so we can write it z into ar, where z is a raised to qh, which belongs to g dash. So the product element x a k y a j can be written as x y z a r, where this product belongs to g dash, and a raised to r, where r is integer lying between 0 and h. So this element is of the type x into ak, so it belongs to g double dash. So g double dash is closure. So now we check the inverse. We will prove that inverse of each element of g double dash, that is also in g double dash. So we choose an arbitrary element. Let x into a raised to k, this belongs to g double dash. Now if k is 0, then the inverse element is just x inverse, and this belongs to, since x belongs to g dash, so x inverse also belongs to g dash, and x inverse can be written as x inverse into a raised to 0, so it belongs to g double dash. So inverse exists in this case. Similarly, if k is strictly greater than 0, then the inverse element is y into a raised to h minus k, where what is y? Y is x inverse a raised to h is inverse, because if we put y here, x inverse a raised to minus h, then it will become x inverse into a raised to minus h into a raised to h minus k, so it is a raised to minus k, which is inverse of this element. Now this y belongs to g dash, since a raised to h belongs to g dash. So this element, whenever h is less than k is less than h, then h minus k, this is also less than h, and this is positive also. So this element also belongs to g double dash. So again inverse exists in g double dash, so g double dash is actually a subgroup of g. Now we want to prove g double dash contains g dash. So that is quite obvious, because by the definition of g double dash contains all the elements of the type x into a raised to k. So for any element x belongs to g dash, that x can be written as x into a raised to 0, which is obviously in g double dash. So this contains g dash. So now we determine the order. We want to prove order of g double dash. This is n times the order of g dash. So let us say m is order of g dash. Now as we take x, which is any element of g dash, so x has m different choices because order of g dash is n. And for this element x into a raised to k, this x runs through these m elements of g dash, and k runs through 0 to h minus 1. That means k has h different choices. So we can write here X runs over m distinct elements of G dash and K runs over the integers over actually n integers 0, 1 up to h minus h integers 0 to h minus 1. So there are m into h different choices for this element x into a raised to k. So we can find m into h different products, actually m into h products of the type x into a raised to k. So if we can prove that all these mh products, these are different elements, then we can say order of G double dash is mh. So let us prove any two products are different. So let us say x ak and y aj, these are two elements of G double dash. So let us assume that they are equal. So let us assume they are equal. Now here this k and j, these are element lying greater than equals to 0 and less than h. Then what is a raised to k minus j? This is x inverse y. Now since x and y, they are elements of G dash, so this element belongs to G dash. And secondly, k minus j, this is less than h because k and j both are lying between 0 and h, so this is less than h. Actually we assume here, because these are two integers, so we assume here j is less than equals to k. That's why k minus j should be positive. So a raised to, since this element belongs to G dash, so a raised to k minus j, that also belongs to G dash. But we know h is the indicator of a in G dash, and therefore h is the smallest element, smallest power of a which belongs to G dash. So this k minus j, this k minus j, since k minus j is less than h, so it should be 0 only. So this is 0, which means k is equal to j. And if k is equal to j, then from this equation x is also equal to y. So it means x a k and y a j, they are same only when x and y are same, k and j are same. So it means these mh products, all the mh products, they are different elements of G dash. So we can say order of G double dash, this is mh, basically this is h into m, so h into order of G dash, so which completes the proof. Now we define characters of a finite group, finite abelian group. So what is a group? What is a character? Suppose G is a arbitrary group, then a complex valued function let us say f on G, that is called a character of G if f has multiplicative property. Which means f of AB, this is fa into FB for all A and B in G. This complex valued function f, this is defined on G, so domain elements, they are elements of G. And second property, and if f of C, this is non-zero for some C in G, that means it is non-vanishing function on G, that means there exist some elements for which this is non-zero. So we have a theorem, if f is a character of a finite group G whose identity element E, then f of E is 1, and for any A belonging to G, FA, this is a root of unity. This is theorem 6.7. So we want to prove f of A is root of unity. In fact, in this case, if A raised to n is identity element of the group, then actually f of A raised to n, that is 1. That means f A is nth root of unity in this case. If order of A is n, then f A is nth root of unity. Now choose an element C in G such that f of C is non-zero, and we can choose this element because we are saying f is character, and if f is character, then it is non-vanishing function. So since C belongs to G, so CE is equal to C, and f is multiplicative also, so it means f of C into f of E, this is f of C, which proves that f of E is 1. And secondly, if A raised to n is E, then it means f of A raised to n is f of E, which is 1. And because of multiplicative property of f of A raised to n can be written as fa raised to n. So this is 1, which means f of A is a root of unity. Now we can say every group G has at least one character, namely the function, constant function 1, which is identically 1 on each element of the group G. And this type of character is called principal character. So if we define f of A is 1 for all A in G, then f is called principal character. And every group has at least one character, namely this principal character. So now we will find out that if G is abelian group and has a finite order, then how many exactly characters are there for that group G. So we have theorem 6.8. A finite abelian group of order n has exactly n distinct characters, which means for a finite group the number of characters is exactly equal to order of the group. So let us prove this theorem. So in the previous theorem we have constructed a subgroup from a given subgroup. For example, let us say for a given subgroup G dash, we have constructed another subgroup G double dash whose order is h times the order of G dash, where h is indicator of any element A in G dash. So from that we can say कि if we choose non-identity element, then at least we get a bigger group from the group G dash. So in this theorem we will just use this symbol G dash A to denote the subgroup which contains x a k, where x belongs to G dash and k is less than h, where h is indicator of a in G dash. Means the group G double dash in the previous theorem, that is denoted by now this symbol. So we can write here where h is indicator of a in G dash. So now we apply this construction repeatedly, starting from the identity group. So let us denote the identity group by G1. Let the identity group E is G1. Now if this G1 is not equal to G, then we can find an element A1 in G which is not in G1. So from this we can define a subgroup G2 which is G1 A1. Means from the given subgroup G1 we can construct another group G2 whose order is h times the order of G1, where h is indicator of A1 in G1. Similarly, if this G2 is not equal to G, then again we can find an element A2 in G which is not in G2. Then we construct G3 which is G2 A2. Continuing this process, we get a set of elements A1, A2 up to A, let us say T, and corresponding set of subgroups G1, G2 and GT plus 1. Because corresponding to A1 we are getting G2, corresponding to A2 we are getting G3 and so on. Corresponding to A2 we are getting GT plus 1. Such that this GR plus 1, this is GR AR for each R from 1 to T. And second property, this is increasing sequence, which means G1 is subset of G2, subset of G3 and so on, subset of GR plus GT plus 1. Now we will assume that the last group GT plus 1, this is equal to G, because G is a finite group. So somewhere this process will terminate, and let us say the last step of this process is G of T plus 1, which is equal to G. Now we prove this theorem by induction. Now we have group G1 which has only one element. So we will prove that there is only one character for G1. And obviously there is only one character, namely the principal character for the group G1. So this theorem is true for n is equal to 1. True for 1. So now we assume that GR has order m, and we assume that order of GR is m and GR has exactly m characters. Then we will prove the theorem for GR plus 1. Now what is GR plus 1? This is the group determined by GR and AR, and let H be the indicator of AR, indicator of AR in GR. That means the smallest positive integer such that AR raised to H is in GR. So we will show that there are exactly h different ways to extend each character of G. Because we know if order of GR is m, then order of GR plus 1, that is m into h. So we want to prove there are exactly m into h different characters for the group GR plus 1. So we will prove that for each character of the group GR, there are exactly h different ways to extend to get a character of GR plus 1. And second thing, we want to prove that each character of GR plus 1, that is actually extension of some character of GR, and that will prove that there are exactly mh characters. Because the first part in which we will prove that every character of GR can be extended in h different ways, to a character of GR plus 1, that will prove only this thing, that there exist at least MH different characters. And secondly, if we prove every character of GR plus 1 is actually an extension of character of GR, that will prove that there exist at the most MH characters, which means there are exactly equal to MH characters. Now any element of GR plus 1 that is of the form x into AR raised to k, where this x belongs to GR and k is greater than equals to 0 and strictly less than h. Now for the moment, suppose there is this possible to extend a character f of GR to GR plus 1. So we can say that a character f of GR can be extended to a character, let us say f curl of GR plus 1. We can assume that character f of GR can be extended to a character of GR plus 1, and as this extension is f curl. Now what can be said about this f curl of x into AR raised to k? Now because we know this f curl is character, so it must have multiplicative property, so this should be equal to f curl x f curl AR raised to k. And secondly, we know this x belongs to G, since x belongs to GR, and we are saying this is f curl, this is extension of f, which is a character of GR. So at any element of GR it should be equal to f. So f curl x should be equal to fx. So it means f curl x into AR raised to k should be equal to fx f curl AR raised to k. Now this thing tells us that if we know this value f curl at AR, then we can define f curl at x into AR raised to k. That means we can define f curl at every element of GR plus 1. So now what are the possible values of f curl AR? So let us take C is equal to AR raised to H. Now we know H is indicator of AR in GR, so it means it belongs to GR. If C belongs to GR, it means f curl at C is equal to FC. And since f curl has multiplicative property, so f curl C should be equal to f curl at AR is raised to H. That means f curl AR raised to H is equal to, because f curl is equal to FC, so this is equal to FC. So f curl AR raised to H is equal to FC, and f is already defined. This is a complex number. So we are saying this raised to H is a complex number. That means this f curl AR, this is one of the hth roots of FC. So it means f curl AR, this is one of the hth roots of FC. Therefore, there are at the most h choices for F curl AR. So there are at most h choices, because it is hth root, h choices for F curl AR. So now we can define F curl. So for a given character f of g, we choose F curl AR to be one of the hth roots of Fc, where c is AR raised to h, and we define F curl on GR plus 1 by this equation, F curl x AR raised to k. This is fx into F curl AR raised to k, where F curl, this is hth root of Fc, and c is AR raised to h. So now h choices for this element F curl AR, they are all different because all the hth roots of unity are different. So if all these h choices are different, it means there are h different ways to extend f to F curl. So now we verify that this function F curl, which we have defined like this, this has multiplicative property, which means F curl of x into AR raised to k, y into AR raised to j, F curl xy AR raised to k plus j. This is by definition f of xy, F curl AR raised to k plus j, and this is fx fy F curl AR raised to k, F curl AR raised to j. So product of these two can be written as f of x AR k, and product of these two can be written as f of y AR j. So this is multiplicative. It means F curl, this is a character, and the non-vanishing property that can be proved by f, because F curl has non-vanishing property because f has non-vanishing property, being a character of GR. Now up to this we have proved that every character of GR can be extended in h different ways to a character of GR plus 1. So now we will prove that two of the extensions, let us say F curl and G curl, they can be identical on GR plus 1, because let us assume that two extensions F curl and G curl, they are identical on GR plus 1 because the functions f and g, they are extended in this way. So if F curl and G curl, they are identical on GR plus 1, where F curl is extension of some character f and G curl is extension of some character g, then since these are extensions of f and g respectively on GR, so f and g should be equal on GR, and that is not possible because these two are different characters of GR. So it means no two extensions of two different characters can be identical. It means there exist at least mh characters for G. And second thing, each of the character of GR plus 1, let us say phi is character of GR plus 1, let phi be character of GR plus 1, then restriction of this phi to GR, this is character of GR, because to be a character we need only multiplicative property and non-vanishing property. So this is also a character. That means every character of GR plus 1 is just an extension of a character of GR. So it means number of characters of GR plus 1, that is just exactly equal to MH, which means there are exactly MH characters for GR plus 1. So theorem is proved by induction. That means number of the characters for a finite abelian group G is equal to exactly the order of the group.